Okay, so we are on the first applied question, question 8, for Chapter 3 of An Introduction to Statistical Learning. This is in Python. I've made a separate video for the R code with the same question. Okay, so here's the question, multi-part question, and we'll go through it one at a time. But basically, we are running a linear regression from a data set called auto. And the auto data set is part of the ISLP library in Python. And we are regressing miles per gallon, or MPG, on horsepower as the predictor. Okay, and so we're going to learn some things about this relationship with our model, and then we are going to see if our model seems to be an appropriate fit for the data. Okay, so let's start by making sure that you've installed and loaded the ISLP libraries, and here's some additional libraries that we'll need to get through the rest of this question, so you can just copy those or whatever. So first we need to load the data set, and so I'm doing that with this command here. Okay, and now I'm going to create my regression, and the way that we do simple linear regression in Python is with the sm.OLS, ordinary least squares, argument. Okay, and I put my y, my outcome variable, and then I put my predictor variables, and then I'm also adding a constant, and the reason is because we need an intercept. And so I'm basically creating a matrix here where in one column is all ones because they all have an intercept, and then in the next column is the horsepower values for each observation. Okay, and so I'm going to print this, and so here is my summary of outcomes. So we're not going to worry too much about a lot of these things just yet, such as the R squared and F statistic and all that. What we're interested in right here is in this table here, okay, these coefficients. And okay, so we want to know, so if we go up to the questions here, we want to know if there was a relationship between miles per gallon and horsepower. We want to know if it's a strong relationship. We want to know if it's positive or negative, and we want a confidence interval for it and a prediction interval. Okay, so let's just walk through this output here. So the coefficient for horsepower is here, and so this coefficient is expressing the relationship between horsepower and miles per gallon. Okay, and so we see that it is a very low p-value, rounds to 0, which means that there's probably pretty strong support for a relationship between the two variables. And that relationship, the estimate of that relationship is this. It is that when horsepower goes up by 1 unit, miles per gallon is estimated to go down by about 0.16 miles per gallon. Okay, all right. Let's see. Okay, so we are also asked to predict what will happen when miles to miles per gallon when horsepower equals 98. So one way that we could do that is we could just plug in the intercept, or constant as it's called here, as well as horsepower, into our formula for regression, which would be right there, the alpha, or the intercept, plus the product of horsepower times its beta coefficient. And so I could do all that, and this would be my approximation. I could also do that kind of longhand in Python, just using Python as a calculator. Okay, I get the same answer, or roughly the same answer, just minus rounding errors here. Or I can use the get prediction function in Python, right? So if I run this, so I get a prediction, right, which is the same as I got here. Okay, this is the standard error of that prediction, and then I get two intervals here. I get this interval, and I get this interval. Okay, so what's going on here? So the first interval is a confidence interval on the on the mean of the prediction, right? So this is saying that with 95% confidence, well, the meaning of a confidence interval is a little bit unintuitive, and I'm not gonna go into the details of it right here. But generally, how it gets thought of, and this is not exactly correct, but how it gets thought of is that the mean of the prediction is somewhere in here. Okay, if you well, anyway, if you're familiar with how confidence intervals really work, you'll realize that that's not entirely right, but it's a decent enough approximation. But anyway, this first interval refers to the mean of the prediction, and the second one is a confidence interval. They're 95% confidence intervals by default. It's a confidence interval for the prediction itself, not the mean of the prediction. Okay, so whereas the confidence interval for the prediction itself, right, is basically saying, okay, well, with the mean prediction plus or minus probably just about 2 standard deviations, right, and I'll get this value. For the mean, I am dividing the standard deviation by 1 over the square root of n. Okay. Yeah, right here. Here, give me 1 second here. I need to fix this in the text. And so anyway, so we see that so that dividing the standard deviation by the square root of n is going to produce a much more narrow interval here, and that's what we have for that interval right there. Okay. Okay, so now we're on to part B. Where's B here? So I want to plot the response against the predictor, and then visualize the line, the regression line, the line of best fit, as it's sometimes called. And so here's my code to do that. So I'm going to, I'm plotting my x and y right here. I'm using a scatter plot to plot my x and y variables, okay, horsepower and miles per gallon, and then I'm going to, and then I'm going to add a line, okay, that is the line of best fit that's taken right from our model, okay, and so this is what we have. So now in part C, we are going to use some additional plots to begin assessing how well we think our regression line, which represents our model's predictions, how well it fits the data. And just with this particular one, with this particular graph, we can see that it might struggle, right? We see kind of a curvilinear relationship with the data, but we're just plotting a normal, or we're trying to fit it with a straight line, and it seems like maybe that might not be best. So anyway, we're going to look at 3 different plots here, and I'll open them up one at a time. If you use R, this is much easier. You can do all of this code here with one command, but that's okay. So the first one that we will look at is residuals versus the fitted values. So the fitted values are down here. So these are different values of miles per gallon. Okay, and then these are the residuals, the errors that the model is making. Okay, so what we see is that there's this curvilinear relationship with the residuals, and also the residuals seem to get more variable as we move to higher values of miles per gallon, and this violates at least one of the assumptions of normal linear regression, which is constant variance throughout the data. Okay, and this does not seem to be fitting that. All right. We can look at a QQ plot, okay, where we are plotting the quantiles of the residuals on the y-axis, as well as the theoretical quantiles from a normal distribution. So the dots are the actual values. The red line is the predicted values if the data was actually normally distributed. Well, that the residuals are normally distributed. That's an important difference. But and we see that our residuals are kind of not really fitting on the line all that great towards the extremes. And so this also suggests that maybe the data is not well approximated with a normal distribution. Okay, now the final one that we'll look at is a leverage versus normalized residuals plot. So this can be a little bit weird to look at. but let's think about it. So the leverage here on the y-axis is representing how much control over the fit of the regression line each point could potentially have. Okay, the normalized so values that have large residuals as well as high leverage have a oversized effect on the parameters that are estimated for our linear model, right? So in other words, so these values right here are not having much of an effect on the fit of the regression line in the context of all the other data. As I move out this way, now I have large residuals, okay, but low leverage, okay? So even though I have a very large residual, these residuals are not having much of an effect on the fit of our regression line, okay? As I move up this axis, the values represented by these points have the potential to very much influence the shape of the line, but they don't because they have small residuals, okay? It is the ones that kind of move into this region, okay, that have both high leverage and high residuals or normalized residuals. And these ones are influencing the size, the shape, the size. They are influencing the parameters that are drawing our regression line more than ones that are in this left-hand corner. Okay, and so we might call these outliers, maybe. And so when we see these values, we have a few options. One thing is we can go to that data and make sure that we haven't made an error in recording that data or transcribing that data. That's possible. Some people are prone to want to throw these outliers out, which can be a major mistake. Okay, so you should only throw out data if you have a good reason to throw it out, and it not fitting the model is not a good reason to throw out data. Okay, because really what this might indicate is that your model is not well suited to the data. So rather than throwing out the data, it often suggests you need to throw out the model and try again. So anyway, taking all 4 of these plots into consideration, it kind of seems that a normal linear regression is not doing a great job fitting this data.